So welcome back to views and indices. Before I start, I must say I wasn't quite happy with myself about the way when I explained this 4x4 matrix with read committed and so on and so on. My question to you, was it clear to you, or do you want me to redo it, just this slide? For whom was it fine? Okay, who wants me to repeat it? Okay, I will repeat it. I saw a few raised hands, just to make clear. So this is the slide that I wish I would have explained better. So this slide has the rows and the columns. So on the rows, you have what you say in SQL about what you're fine with and what you're not fine with. On the columns, you have all the bad things that can happen, right? So dirty reads is you see values that have not even been committed by other people. Non-repeatable reads means you keep reading the same thing, but the value is different every time. That's a non-repeatable read. Phantom read is when you have you read a table multiple times and you have new records that pop out of nowhere that other people committed. And serialization anomaly is you notice that you're not queuing, like it's not everybody taking turn. And so basically, when you say set transaction isolation level read uncommitted, what you're essentially saying is, I don't care about anything. I don't care about serialization anomalies. I don't care about phantom reads. I don't care about non-repeatable reads. And in the SQL standard, basically, I don't care about dirty reads. And this little thing here is that in spite of the fact that you don't care, PostgreSQL will make sure they don't happen. So this is why here. Then read committed means I don't care about not taking turn. I don't care about extra records to appear. I don't care about reading a different value every time. But I do care about dirty reads. I do not want any dirty reads ever. Then you put that. Then the third one, if you say set the isolation level to repeatable reads, what you're saying is I don't care about serialization anomalies. I don't care if it's not like we take turns. I don't care about phantom reads, so I don't care if there's new records that appear out of nowhere. However, with PostgreSQL, even though you don't care, they will not happen. So with that level, you will not get any phantom reads in PostgreSQL. But if you say repeatable read, then you care about that. You do not want ever to be in a situation that if you reread the same place, you see a different value. You want the guarantee that if you keep reading the same place, you will keep seeing the same value. Right? So that is something important to you. And you also care about not having any dirty reads. And now the highest possible level, if you say transaction level serializable, is no dirty reads ever. No non-repeatable reads ever. If I keep reading the same place, I want to see the same value. No phantom reads ever. If I look at a table, I want it to be the same. I don't want to see new records that pop out of nowhere. And I'm also not fine with the serialization anomaly, meaning that it should be as if we were all taking turns and I was the only one using the database, right? So this is what it means. Does it help? Yeah, awesome, perfect. So I just wanted to have that to make sure that you understand. So now I'm going to come back to use an indices, which is this one. And I was on 19, this one here. So I gave you all of these queries, and we noticed that there's a lot of repetition because there is this query select star from publications where author is Albert Einstein. It's all over the place by itself over there, but also appearing, as you remember, these are nested queries. It's nested inside something else, nested in here, and so on. So these are all nested queries. In fact, if I have a query like this, it would be nice that I could just give it a name somehow, that I could say, okay, now let me give that name, and then I can refer to it by name. Then I can just put it in the from clause, right? So if I had a way to call the results of that query publications by Einstein, and then I can just say from publications by Einstein, That would be convenient, right? And in fact, we can, and that's called a view. And so you can give a name like this to a query with the command create view, called publications by Einstein, as, and then you put the query you want. Okay, this is called a view. And so now, what it means concretely is that I can just use that new name that I have in here instead of copying the query everywhere. For whom is that clear? Right, so this is called a view. So if you want to query it, just use it in the from clause, and now this is going to give me a select title from this, and then I get this projection. What is very important is that this is dynamic, meaning that if the original table changes, and so the view would change, then it does change, right? So you keep seeing the updates. The view is following the changes. You don't take a snapshot and then freeze it. It's not like that. You follow the changes. So it's always visible. What you can also do in a view, if you don't like the column names, which would be those of the original table, you can rename them. You could, for example, say that you want the projection to title and year of the publications by Einstein, and then you just say, I call it T and Y, and then you create a view that has this name with T and Y as the column name, so that you can also adapt in the view. So what does that tell us if I zoom back now, if I take a step back on the relational databases? You know that we can have tables that have a name. These are the ones I created with create table. And I gave a schema. I told the columns, the types, and so on, and then I put data in there. These are the persisted tables. These are the ones that PostgreSQL stores on your local drive forever. You shut down the laptop and switch it on again, it's still going to be there. So these are the persisted tables. Then you have the views. So the views are the data that is, you only give a nickname to some predefined query. It has a name, but by default, a view is dynamic. It's not persisted in any way, it just follows whatever the data is, right? And then you have the on-the-fly relations. These are the ones that appear in your notebook, right? You type a query in your notebook, you see the results. They don't have a name. These are just the results of your queries. Okay, so we have these distinctions between all sorts of tables. And what happens is that depending on the kind of view or the kind of relation, so you have the persisted tables, they have a name and they are persisted. The views have a name, but they are not persisted, they are dynamic. And on-the-fly relations do not have a name and they are also not persisted. But now you saw an extra row that appeared suddenly in this table. It's a special kind of view that is called a materialized view. What is a materialized view? It's an optimization. It's the idea that to make it even faster, you take a snapshot, like with a camera, you take a snapshot of the table and you actually persist it to disk, right? And if you know that the data hasn't changed, then that persisted view is still up to date, right? So instead of executing the query that is associated with the view every time the view is used, you just read it from the disk as though it had been a persisted table. For whom does that make sense? But there is a price to pay. There is a price to pay because what happens if the original table gets updated and the view is supposed to change? So there's two ways to handle it on the, like, I'm not talking about specifically PostgreSQL. The first way to handle it is to say that whenever there is a change, you just update the persisted view. You make sure you keep it up to date. So every time there's a change, you propagate it to the persisted view. First approach. Second approach, you say, well, I don't care if the view is not up to date. You know, you took a snapshot, and if there's new data in the original table, you don't really care. You just continue with the snapshot that you picked a day ago, and maybe every day or every week you will update the materialized view. So this is the other approach, right? So this is called the materialized view. Okay, for whom does that make sense? Right? Yes.
why not update it only if the table has a new version and we need it? So why not update as needed?
That is also absolutely. This is a good point. This falls back to the optimizations. It's the conversation we had at the break. Imagine that you make the promise that every time the original table gets updated, you propagate to the view. So my question is, if nobody queries the view, will you actually notice if I don't do it? Nobody will notice, right? And this is one of these examples where the database engine can do whatever it wants as long as nobody notices. So in fact, even if you say you update the view every time there is an update, it would be fine to do it only if somebody asks for it because nobody will see. So if nobody will see, you can absolutely optimize in this way. That makes absolute sense. Does it make sense? Okay. Now we can update a view, but in another sense, not in the sense that we propagate the changes from the original table. In the sense that if that were a table, I could just edit the values or change the values or delete some records or insert records, right? Can I do that to a view? The answer is yes, sometimes, under specific circumstances. So imagine that here, you take a view and you want to insert a record, Albert Einstein foo 1920. What do you think should actually happen if we try to do that, if the intent of the user, if they modify that view? Exactly, you propagate to the original table. Can we do that in that case? We can, right? It's just a selection on the original table. So in that case, we would just take that tuple and also add it to the original table. Now, what it really means to update a view is we need to find a way to update the original table in such a way that by applying a view, I see these changes. So it's an indirect way of applying them. You basically interpret the query as the user that they want to see the view change as if they had inserted a tuple. And you do that by inserting them in the original view, and then they will pop back into the view. For whom does that make sense? Right? So that's something that's perfectly fine to do in some cases in PostgreSQL. You can use insert into the view, and that will propagate. That works. And so what you do is, in that case, you just insert it to the original view, this foo, Albert Einstein foo 1920. Yeah. So you can do insertions, you can do deletions, you can do updates to the views. And when it works, PostgreSQL will figure out a way of propagating it to the table. This is an example where it does not work. If you, for example, you have a view that is not just a selection from a table, but it's something more complex. For example, it's a join from two tables in that case. And now you try to insert a tuple in there to the join. Then the problem in here is that when you have a join between two tables, it has some functional dependencies in there, right? Because it was a join. So a joined table has a specific pattern in it. And so if you just insert tuples into a joint table arbitrarily, you can insert whatever you want, it's no longer a join. So you cannot just modify the original tables in such a way that the join would give you an inserted tuple. That doesn't work, right? Does it make sense? So this query is too complex. We cannot find a way to update the underlying tables in order to make changes to it. So that doesn't work. This one doesn't work because in that case, you only project two titles. You would be missing the year in that case, right? So if you just insert a title, you wouldn't know what year to insert. But can you figure a way that we could make it updatable? What condition on the underlying table could we have that we could apply such an update?
Yeah, there is a question from Zoom. What's the difference between the view and with clause?
The views then?
With clause. I mean, when they want to like use query to select from the other table, sometimes they will create with it's like try to create a table and you can
maybe I should look.
directly-
Let me
yeah.
see. Maybe I need some offline investigation on this.
Mhm.
Oh, the with clause. Ah, I see. No, so the with clause would be you use the with clause and then you use the view you create in the with clause. But when you create a view, it's forever. That's the difference. If you do create view, you can use the view for as long as you want. If you use with, then as soon as you're done with the query, it's gone. So with is more of a shortcut to write the query in a way that is easier to read. But if you want to reuse the view in thousands of queries, then you need a view. That would be the difference. Does it answer your question? Yeah, awesome. So now, coming back to this query. The reason I cannot update this view is that my original table has 3 columns. So the first one is Albert Einstein. The second one is the title that I want to update, but then I have a third column that is the year. And so the problem is that if I try to update this view, I would only update the title, or I would only create a new record with a specific title. What do I put in the year? Right? This is why it's not updatable. But what could I change to the schema of the original table to make it updatable? What could I do? In which cases will I know what to add to the year? Yes? Exactly. You provide a default value. If you provide a default value or you allow null, you make it not null, nullable, then in that case, you can update it, right? But it's if the schema allows you to do that. So if you look at the PostgreSQL documentation, they are a bit restrictive. So the only cases where they promise that they can update the view is first, you have only one table, you're not joining or anything, just a single table in the from clause. Then you need to have all its attributes in the select clause, except those that have a default value or can be null, because these you can just populate with the default value and be null. But all those that are not null and that don't have a default value, then you need them in the select clause of the view. And then you cannot do anything fancy. So for example, imagine some complex query where you have the relation and it reads itself in the where clause, right? For example, an argmax kind of computation, right? Selects everything where some attribute is equal to the max in the entire table. So here you would have a complex query that refers to itself in the where clause, and that is also not allowed. So keep it plain and simple, basically, and in that case, the view is going to be updatable. Who is with me? Okay, so the views are really nice if you want to give them a name and reuse them in the from clause. And if you want more performance, you can also use materialized views that would take a snapshot of the view and make them a bit faster. Which brings us to the second part of what we are exploring, the second part being indices. They kind of go hand in hand. In some way, you could consider that indices are kind of views, or views are kind of indices. It takes a bit of a stretch, but if you think of it mathematically, conceptually, they are very related to each other. Because in fact, these are additional structures that we add on top of the table. This is what they have in common. The goal of the indices is to make the query fast. Who has ever seen at the end of a book, you buy a book and at the end of the book, there's an alphabetical list of words, and then you can look them up and find the page. Who has ever seen that? That is an index. We do exactly the same thing with database systems. That's exactly what an index is. Technically, I could just say goodbye and go, and you know what an index is, right? But let me still show you how it's done in PostgreSQL. So for some kinds of queries, we are able to make them faster with something similar to this index at the end of the books. So this is a selecting query, right? I have some predicate in the where clause, and so I select the author that has to be Albert Einstein. Now, how do I execute a query like this? The only way I can do it, naively, is to read all the records, right? I need to look at all the records, and I need to see, is that Albert Einstein or is that not Albert Einstein, right? That is called the full scan of the table. So I basically go, I don't know if, do I have an animation? Yes, I do have an animation. Fantastic. So what PostgreSQL would do is it looks at the records one by one, and either it keeps it or it doesn't keep it. First one, Albert Einstein, check, keep it. Second one, Albert Einstein, check, keep it. Third one, that's not Albert Einstein, we don't keep it. Fourth one, that's Albert Einstein, we keep it. Fifth one, that's not Albert Einstein, we don't keep it. Here it's Albert Einstein, we keep it. Albert Einstein again, we keep it. Not Albert Einstein. Albert Einstein. Not Albert Einstein. And Albert Einstein. Now we can return these query results. But did you notice how it took forever? And if I have an even bigger table, it's going to take even more time. In fact, there is a whole area that is taught in computer science that is called the complexity theory. Who has ever heard of that? Complexity theory. It's basically, if you increase the size of a problem, how much more time is it going to take? In that case, do you agree that if I do a full scan for this, for executing my query, do you agree that if I take a table that is 10 times as big, then it's going to take 10 times as much time? Do you agree with that, right? This is called linear complexity, right? The time it takes is proportional to the size of the table. We also call it, you might have heard of O of n, basically as the complexity, where n is the size of the table. So linear is kind of okay, but if you have 1 billion records in your table, then that's too much, right? Imagine, just to give you the equivalent, imagine that you buy a book that has 1,000 pages, and you look for, I don't know, the word thermodynamics. Then you look at the end, there is no index. What do? You have to read the book. You go through the book, you read the book, and the time it takes is going to be proportional to the size of the book. If the book is double the size, then you need double the time. So this is linear. That's not good enough. Database people are not happy with that kind of thing. This is just taking too much time to do, and especially if there's billions of records, this is too slow. There are cases that are even more frustrating than that. So let's now, instead of looking at the author, we're going to look at the title. So we have this query that is a selection. We look for the title, the theory of relativity. So I'm going to go through each by one, the records. It's linear, so it's going to take a while, right? I look, okay, the first one, is it the theory of relativity? No. The second one, neither. Neither, 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 neither. At last, now we have it. Now we can report it. So here is even more frustrating because you're basically taking forever, even though it's just one tuple. You just need to find one tuple. And if you have in mind this alphabetical list of words at the end of a book, this is better than linear, right? You don't need to read the whole book. You just look it up in the alphabetical list and find it. So we need to do something about it. We have to find a way to execute that faster. In fact, just to give you the order of magnitude, a modern database system is able to give you the tuple, even if there's 1 billion records in the table. It's going to give you the result of a query like that in 1 millisecond, 1 or 2 milliseconds, very fast, even with 1 billion records, just to give you the order of magnitude. But this is because we use indices, and that's exactly what I'm going to show you. So can we do better? Yes, obviously, because otherwise I wouldn't be teaching a lecture on that topic. So the first idea, imagine that now I give you this table, and I ask you to locate the title Mathematical Logic. Did you find it? What did you do to find it? Who did a full scan? Who was more clever than that and did not do a full scan? Can you tell us? Did something help you in that process? Something particular about that table? But then you did a full scan, right? Your eyes did a full scan. Yes. Oh, that's clever. So that's indeed a human might do, maybe artificial intelligence. So you basically looked at the size and you look for the small. Yeah, no, that's a clever trick. That's a clever trick. I had something else in mind. In fact, do you notice something on the titles? It's in alphabetical order. You see? A, C, D, M, O, T, W. It's on an alphabetical order. So can you do faster than a full scan in that case? What do you do when it's in alphabetical order? And how do you do it? Like, how do you look up a word in a dictionary? If I give you a dictionary that large and you look up a word, what do you do? Yeah, how do you do that? But how do you locate it in the dictionary? So you already kind of interpolate. So yeah, what if you didn't have, meaning it's an unknown language, and it could be that there's a lot of words with the letter A and less with the letter N, so you cannot make any assumption on that. Do you have another way to still locate it? Or you? A binary search, exactly. In fact, this is what you probably see it in primary school. I don't know do you still teach how to look up words in a dictionary in primary school? It's not done anymore because we have computers and we just type them. When I was a kid, they would teach us how to look up a word in a dictionary. And the way you do that is you open the dictionary in the middle at random, and then you look, okay, am I too early or too far? And then you cut it in two again, and you just like this every time narrow down where you have to look for it. But that you can only do when it's sorted. And the name that it has is, as you indicated, a binary search, right? So I'm going to show you here how we do a binary search. And in fact, if you think for it, this is how you look up a word in a dictionary. Before you had computers, because now obviously you just go to a website and type the word and it finds it for you. But that's because it has an index that it's able to do that. So here we spotted it directly. I mean, for us humans, it's maybe easier. So binary search. I just look at a record randomly, but roughly in the middle, right? And then I ask myself, okay, is that before? So is what I'm looking for mathematical logic? Is it before or is that after that record? Well, O is after M. M is before O. So I know it's going to be before that. So what I can do is that I can throw away the second half of my table. So everything that's below, I can ignore now because I know it's sorted. So I can ignore that. So you see that it's already better than a full scan because I will not even look at them. In a full scan, I would have looked at them. But here, I don't do that because it's sorted. And then I again pick it at random here in the middle. Now we have D. Is M before or after D? It's after D, right? So now all that part above, I again ignore it. And then again, now it's before. And now I have that left, mathematical logic. We notice that it's faster than a full scan. Faster than a full scan. By any chance, I don't expect everybody to know it, but I'm sure some of you know what is the complexity of that, the algorithmic complexity. Yes? Log n, exactly. It's a logarithmic complexity. Let me explain what it means. In the linear complexity, I explained to you that what that means is if the table becomes 10 times longer, then the time it takes is 10 times the time. right? That's linear, right? It's the same number. Now, what it means that you have a logarithm complexity. I'm going to give you an example of logarithmic complexity. If I read a table and it takes me, let's say, 2 seconds to read a table. Let's say it has 100 records. Now, I have 10 times as many records. If I have algorithm complexity, it's going to take me, let's say, 1 more second. So if I decouple, if I have 10 times the number of records, 1 more second. If I again have 10 times more, so I was at 100, 1,000, now I'm at 10,000. Again, 1 more second. 10 times more, 100,000, 1 more second. 10 times more, a million, 1 more second. So you see what happens. Now, if I multiply the size of the table by 10, it's not going to take me 10 times the same time. It's going to take me a constant number of additional seconds. That is called the logarithmic complexity, right? It basically means that it's not proportional to the number, but it's proportional to how large it is to write the number. It's the number of zeros, right? It's proportional to the number of zeros that you have in your number, right? Does it make sense? That's an algorithmic complexity. And the reason it's algorithmic is basically, let me take the example not of multiplying the table by 10, but by 2. Imagine that the table, I did that. Now I take a table that it's twice as large. How many more steps do I need if it's twice as large? 1 more step. Because if it's twice as large, I'm going to be looking at the middle of that twice as large table. In 1 step, I already drop half of the table again, and I'm back to the original size. So if I double the table, I only need 1 more step. If I double it again, I still only need 1 more step, right? And that actually we love in computer science. Do you know I don't know the name of that problem, but there was in antiquity somebody who wanted a reward from a king, and they say you take a chessboard and you put one grain of rice on the first cell, and then you double it at every cell, right? So you have 1, 2, 4, 8, and so on. And then if you do the count, when you arrive at 64, it's like an absolutely gigantic number. That is the power of doubling. You only had 1 more cell, but it doubles every time. Logarithmic is the opposite. It's when it doubles, you only add a constant number of steps. So this is why we love this idea. We love this idea because that's going to scale. You can now have a table with 1 billion records or with 1 trillion records, but every time you add a 0 to the number of records in the table, it only adds a few more steps. So that we absolutely love in databases. For whom does that make sense? Right? So this is the logarithmic complexity that we absolutely love in databases. So in fact, another way of looking at the same thing, it's exactly the same thing, is like a tree. So if I redo what I've been doing here, but imagine that I have organized my records here as a tree like that. The one that is in the middle, I would put at the root of the tree. Then everything on the left was the first half here, and everything on the right was basically the second half. And then I look, is it bigger or smaller? It's smaller, so I go to the left. I discard what is here. And then I again have something that is in the middle of the higher part. This is basically what happens. So this is I was at the root of my tree, discarded the right part of the tree, and then I again go to the middle, drawn from the phenomena of capillarity. And when I do that, I'm here, basically. And then again, I cut it in 2. Is it before or after? It's after. So I drop that part. I go here, and then mathematical logic. So what I want you to see is that this is twice the same thing that I'm doing here. In the first case, if I rewrite, I just split it into every time, right? Select the half that I want. Who sees that this is the same thing? I go on the left or on the right every time, comparing until I reach it. Who sees that it's the same thing? This is a tree structure. It's called a tree. In computer science, a tree is very popular in the field of databases, but we also teach that in algorithms and data structures. Because when you have a tree like that, it's a binary search tree, in fact, in that case, because it's such that everything on the left comes before that alphabetically and everything on the right comes after that. And so basically, you can implement the binary search, what I explained, with going left and right. You basically go down the tree until you find what you're looking for. And in fact, when we build an index in a database system, we actually build a tree like that. This is one of the ways that we can build an index. Now, of course, if you compare that to what there is in a book, imagine that everybody in the world were a computer scientist, then probably at the end of the book, you would have a tree instead of an alphabetic list of words, right? They would basically facilitate for computer scientists and geeks, that would be awesome. But it would probably be too complicated, so they put an alphabetical list of words, and in fact, they delegate to you the binary search. You as a human have to find your way in the alphabetical list. But when you have a database system, we build a tree like that to actually do the binary search. And you can see how it's logarithmic, because when you look, if n is the total number of records in the table, the total number of nodes in there, the log n, so the logarithmic complexity, comes from the fact that what you touch, what you look at, these are the ones that are colored, is log of n, roughly. So when all of that is n, what you have on a single path is log of n. That is why it's magic. You don't actually look at anything that is outside of that path. Okay, then that corresponds to the table. So it would be wonderful if in PostgreSQL we would implement something like this, and whenever you look it up, you just go down the tree and then you have the pointer to the original table. That's an index. That's exactly what we do in practice. So of course, it's a bit simplified because the trees that we build for database systems are a bit more complex than that, and I will show you how. But before I do that, I would like to show you something else than a tree. There is another kind of index that doesn't have logarithmic complexity. It has even better than logarithmic complexity. It has constant complexity. Who knows what constant complexity means? O of 1. 1, 2, 3, some of you. It's magic. So can you tell us what constant complexity means? Anybody? Yes? Exactly. It doesn't matter how large the table is, it's just the same time. The table can have 1,000 records, takes 1 millisecond. Can have 1 billion records, still 1 millisecond. Can have a quadrillion records, still 1 millisecond. This is a constant complexity. It's O of 1. So it sounds like science fiction, like how can we even do that? How can you even build something that even with a quintillion records just output in constant time? It sounds like that cannot even exist. And in fact, it does exist. It absolutely does exist, and that's called the hash index. So here's how it works. I have a table. Of course, I don't have a quintillion in there. I only have 6, but that's just for illustrating what I'm about to show to you. So we are going to build a hash index on that table so that then we are able to very quickly, in constant time, find the let's say, the century in here. So what I'm going to do is I'm going to take a function, it's a mathematical function, that I'm going to call h. H is called a hash function. You have to think of a mixer, or how do you do a smoothie, you know, with this, you just put the fruits in there, push a button, and it all mixes everything. This is what the function h does. In fact, that function h is going to eat whatever you feed it with, and it's just going to do a bunch of addition and multiplication and spit out a number. It's called the hash function. The function is very efficient, and it just takes a constant number of time, just a bunch of addition, multiplication, and modulo. So what happens is that if we call that function h with 20, it just happens to give us 0, right? It's just whatever it gives us. It can be any function, it doesn't matter, but it's some function. It's deterministic, meaning that if you keep feeding the same input, you get the same output, right? There's no randomness in there. So let's say that h of 20 gives us 0. So we are going to put the 20 in the 0th position. You know, computer scientists, they love counting from 0 and not from 1. So position 0 is the first one here. So I put the value of 20 plus a pointer to my record. So far, so good. And I do it again. I told it's deterministic, so it's again going to be 0. I add a pointer. And now h of 19, maybe it's going to give me 4, right? Then -4 gives me 3, so I put it in there. -6 gives me 1. And 20 is again there. Now, these hash functions, they're actually very useful in cryptography for encrypting things and signatures. It's kind of a paradox in itself because that function is basically deterministic. If I feed it with 20, it's always going to give me 0, for example. But it looks random because the way that it actually gives you the numbers is a bit random. It just spreads them all over the table in a way that seems random, right? So this is one of the features of hash functions. So it's going to basically spread it all over that hash table. It's called the hash table on the left. What is very important is that this here is my relational table. This is what I have stored in PostgreSQL. This is my actual data. What is here is something additional, invisible, that is created by PostgreSQL, but it's hidden. The user doesn't see it. But PostgreSQL knows that it exists, and now it can use that in order to accelerate the queries. Now imagine that I receive this query, select star from scientists where century equals 19. So if I hadn't built the index, that would be a full scan. I would have had to go through the whole table, linear time, linear complexity, and we saw that's not good enough. Can anybody explain to me how I can use this additional hash index to make the query faster than a full scan? Yeah? Yeah? Yes, so assuming you find the 19, then very quickly you locate the record. So that part I agree. So imagine you know how to arrive here, then you follow the pointer, that is constant time. You have the 19, you go there. But how do you know where 19 is? It's actually an easy answer, yes? Exactly, you compute hash because you have h. So the hash function, you do have it. So you just compute h of 19. Again, it's a bunch of addition, multiplication, and so on. And h of 19 is going to give you 4. This is also a constant time. It's again, just simple arithmetics. And now you know how to look up in the table at position 4. That is because this is in the memory. And in the memory of a computer, we call it random access memory. That's why it's called RAM, random access memory. That means that the time it takes to look up at any place in memory, if you know where, is constant. That's what random access memory is. So in constant time, we can compute h of 19. In constant time, we look at it in memory. We look at the pointer that is next to it. And in constant time, again, we know exactly where to look. If it's on disk, then it would tell you where on disk we look. Who sees that it doesn't matter how big the table is. I could have a quintillion records in that table. It's still constant time. I compute h, locate the position in the hash table, and follow the pointer, right? But there is a price to pay, is that if I have a table with a quintillion records, first, do you agree my hash table is going to be gigantic? So I will need more space. I will need space to store that hash table. It has a cost. It's not a free lunch. So it has a cost in space. Second, do you agree that building the index is going to take a lot of time? Right? It's not the same to build the index and to use the index. Using the index is easy, it's instant, but building the index requires a full scan. When you build an index, you go through all the records. And so that's a cost you need to pay for the index in terms of additional space to store the index, and in terms of additional time to build the index and to also maintain the index, because if the table changes, you need to update the index at the same time. Who is with me? Right? Awesome. So that's the magic. In constant time, we can actually do a lookup query. So this is for queries that don't return a lot of tuples, for those that are highly selective. And yeah, that's an index. So next week, I'll continue. I will come back to the trees. I will explain to you how, in fact, we don't use binary trees. We'll look at something that is slightly more complex that's called the B+ tree. But I'm going to explain B+ trees to you next week, how it all works and why it's actually useful. even though they have logarithmic complexity. So thank you very much, everybody. Enjoy the exercise sessions, and I'll see you next week for the B+3s indices. Thank you very much.